And we're live. Hi, everyone. My name is Cecil Phillip, and welcome to On.NET Live, where we talk about all the cool things that are happening within the .NET ecosystem. Today, especially, I'm really excited because we get to talk about one of the projects that I've been paying attention to over the past couple of months. And I hope you're going to like it because I think this is really cool. And that is Microsoft Orleans. And with me today, I have my friend Reuben, who's from the Orleans team, who's going to talk to us about it. So, Reuben, why don't we start off with you just telling us a little bit about yourself, who you are, and like what do you do here at Microsoft?
Hey everyone, I'm Reuben Bond. I'm lead engineer on Orleans, and I love distributed systems. So we're going to talk a lot about them today.
Nice. Yeah, I'm really excited to talk about Orleans. And, I feel like a lot of folks don't really know that Orleans even, is so powerful in some of the cool things that it does and some of the project that, that kind of use Orleans in the background to do what it does. But we're going to get into that. I don't want to give away too much of it. First, I want to switch over to my desktop and I want to share some links with everyone so that we could, quickly get everyone up to speed about what's going on. So I'm going to share my screen. All right. So first thing I wanted to talk about, .NET Conf Focus on Windows. That was last week. It was a great conference, tons of great content about building desktop applications with .NET. If you did not get to see it, all the recordings are available now on YouTube and on Channel 9. So I definitely recommend you go and head over there and check them out. We had a ton of great speakers. We had content about building Blazor apps for the desktop. They talked about building apps with SignalR Service, modernizing apps with Visual Basic and .NET 5. Like, it was really cool. Definitely recommend you go ahead and check out the recordings of those. Next thing I wanted to talk about really quick. So John Galloway, he had a really cool blog post that kind of summarized what we did for Web API in February. So the entire month of February on .NET's live TV, we talked about Web APIs. And so as we kind of scroll through John's blog post, he mentions the Let's Learn .NET Web API live workshop that we had. That was really cool. We talked about like all the different blog posts that our buddy Brady Gaster wrote. And then also, on this community stand-ups and on the Microsoft Doc show, there are tons of great things about Web APIs. So we had a whole Web API month. So again, if you missed any of that content, I definitely recommend you head over to the .NET blog and take a look at John's blog post. And he kind of summarizes a lot of that cool stuff that we created. Next thing I wanted to highlight last night. So exactly last night, like March 3rd, just 23 hours ago, we released a new beginner series again about web APIs. And this is really focused on people that may not be familiar with ASP.NET Core. Maybe you just learned C Sharp. Maybe you haven't really built a lot of production level applications. But hey, I want to know what web APIs are for. What are their benefits? What are some examples of them? So this course kind of walks you through them in some really short beginner friendly videos. Again, this is also available on Channel 9 and on YouTube. So go ahead and check those out as well. And the last thing I want to share with you. So one of our coworkers, Julio, he has on YouTube, out of the kindness of his heart, created this really in-depth look at building RESTful APIs with .NET 5. You might see a trend here, right? You might notice everything that I'm talking about has to do with web APIs. But like I said, it was Web API February. But again, I definitely recommend you head over to Julio's YouTube page. Look up for the .NET 5 REST API tutorial. Hit subscribe, watch his videos, and definitely give him some feedback. Let him know what you think about it. All right, now that we got that out of the way, Reuben, let's talk about Orleans. So
Cool.
can we do like a quick elevator pitch? Like, what exactly is Orleans, and like, what are the problems that it aims to solve?
Okay, so Orleans is a framework for .NET for writing mostly large-scale distributed systems. So anytime you've got an application and you want to be able to make good use of your hardware and take away some pressure from your databases, for example, Orleans allows you to write those kinds of applications in an easy way. And we'll talk more about it. I'll try to motivate the reasoning behind Orleans and how it helps to solve some of the problems that a lot of application developers run into. So we'll kind of build that up.
Got it. And I know, so this week was Microsoft Ignite, and I know a lot of different products were announced, but particularly Microsoft Mesh was announced. And I
Mhm.
saw you posted a message saying that Mesh actually uses Orleans under the cover, right? Is that true?
Mhm. That's right. So Mesh uses Orleans as well as SignalR in conjunction with each other. So Orleans mostly in the further in the backend place, and then it communicates via SignalR back down to the user. And so those things hook up quite nicely. And so we'll kind of talk a little bit about how exactly that might look, but mostly leave it to your imagination, I guess.
Nice. And so could you mention some other products that might be using Orleans? Because I think it's good for
Yeah,
folks to realize that this is a real project and people are using it to build real applications.
yeah, sure. Well, the canonical example has always been the backend services for the Halo games and Gears of War. Skype Consumer uses Orleans for some things, and Microsoft Teams as well for some other things. PlayFab, so a lot of online multiplayer servers. Those are all scheduled and managed by Orleans, as well as in-game monetization, so in-game economy things. Azure Machine Learning, Azure Quantum are also on Orleans. And there's a Dynamics 365 fraud protection is another one. So Orleans in that case is used for detecting and preventing fraud. There's a bunch of other cases around Microsoft where we use Orleans internally, as well as cases out in the open.
Got it. And then I know we usually refer to, or you've referred to Orleans as a virtual actor framework. Like I've seen that in the
Mhm.
documentation and some of the YouTube videos and stuff like that. Now, I have a computer science degree, but my degree
Yep.
never told me anything about actors. I learned about object oriented programming. I learned about layered architectures and diagrams and UML flowcharts and all these types of things. Never taught me about actors. So explain to my old brain, like, what are actors and how is that different from how we usually think about constructing like an application?
So actors are this model that was defined actually in the early 70s by someone named Carl Hewitt.
Mhm.
And it's this kind of model for modeling concurrency. In Orleans, we kind of keep the word actor for the research papers. So we say, all right, technically Orleans implements what we termed as the virtual actor model, which is actually a lot more just like objects. So you have objects and they are around when you need them and they go away when you don't need them. But they're single threaded. And so, because they're single threaded and you can communicate with them from anywhere in a whole cluster of application instances, they're essentially like actors, right? So they fit the definition of an actor, but they kind of take it further into this other thing called virtual actors. But as far as application developers are concerned, you don't really need to think of the word actor, right? In fact, during all of this, I don't think I intend on mentioning actor really even once. We just call them grains or
Okay.
potentially cloud native objects or something along those lines.
Is there a reason behind the name grains? Because when you say grains, I just imagine little specks of stuff scattered all around. So
Yeah,
is that the analogy? Like grains are like little specks of services that are scattered all
yeah.
around the
You
cluster.
you can think of it kind of like how an object encapsulates state and behavior.
Mhm.
Well, a grain also encapsulates state and behavior. But when Orleans was originally designed, they wanted some other kind of term so that you don't confuse them with objects in the local process sense. So really, grains are kind of more like a distributed object or cloud native object. They're an object by most meanings of the word, but they are accessible from anywhere, and so they have most of the same semantics as objects. But also, there's a few things you need to tweak when you want to take an object in your process and make it accessible from anywhere. So you can treat your entire set of processes or your application instances like one machine. And so we made a unique term, grain, for that.
Got it. Okay. And so Orleans now, so I could create grains. I can create like these specks of distributed things that kind of live in my
Mhm.
ecosystem. So when I think about that, I automatically think, okay, well, we're talking about building distributed applications, and then that means that we're talking about microservices, which means we're talking about cloud native and all these other terms that kind of start to pop into my head. And so I feel like I'm guessing like something like Orleans could help me go from on premise, building a somewhat distributed application on premise to probably to the cloud to Kubernetes, right? Is that
Mhm.
is that something that we could do easily, or is it something that I have to rewrite a lot of my code to
Oh,
kind of make happen?
definitely. So you don't need to change your code when you write an application in Orleans. You can write it for a single machine that runs, when you hit F5 in Visual Studio, for example,
Yeah,
or on a server somewhere in your data center or on premise, and scale it out to the cloud on Kubernetes or Azure App Service or Service Fabric. And you don't need to change your application for that. It's just a little bit of config that needs to change. And so internally at Microsoft, we're running Orleans on Azure App Service in production, on Service Fabric in production, on AKS, Azure Kubernetes Service in production, and even on traditional cloud services in production.
awesome. So, I mean, I have tons of questions, and so I could sit here and ask you questions
Yeah.
about Orleans all day. But why don't we start diving into some of what you have to share with us, and so we could, kind of get an understanding about like the underneath the details about how Orleans works.
Yeah, definitely. Okay, so today we're going to talk about how Orleans works mostly under the covers, and it's not going to be demo heavy, but there's going to be a bunch of code snippets and a lot of diagrams. And so questions are more than welcome. We can interrupt this anytime and try to answer those.
Mm.
Now, before we talk about how Orleans works, before we answer the how, we need to really answer the why. Like, why is Orleans that way? Why is Orleans structured in this way? And what problems does it solve? So once we understand that, it kind of motivates a little easier why we're doing all these things. Some people use Orleans just purely because they like the programming model. They like using grains to structure their application. They like that way of thinking. But the fundamental problems that Orleans solves are really what makes it popular internally at Microsoft and outside.
Got it.
So the question is, but why? Now, to answer that, let's start by saying that you're building a web application. You've got this typical kind of architecture where the internet talks to a load balancer, it talks to a bunch of different application instances here, and then they all talk to a database. And so anytime you get a request, it goes through your controller, maybe you've got an ASP.NET controller, and makes a read request on the database, or maybe it's a write, and it then goes and answers back. So that's fine. And we have multiple instances of your application. First of all, because we might have a lot of load, but also because we want to have some redundancy, right? When one of these things goes down for whatever reason, we don't want any downtime from the user's perspective, right? So we have multiple instances of that. Now, there's a few problems with this architecture. First of all, when we're hitting the database for every single request, that ends up adding some latency to our application. Secondly, because we're hitting the database on every single read request, we're also putting undue load on the database. And really, we should be trying to free up the database's CPU and memory cache for serving writes instead. And then finally, because we have these multiple different instances of the app, they don't know about what each other are doing. And so if this instance on the left here goes and writes to the database, and then this one on the right also tries to write, if they're talking about the same row or the same key in that database, you might end up with a write conflict. And so that causes tension in here that the database needs to resolve if you're using, say, transactions or something, or that the application instances need to resolve if you're using something like optimistic concurrency. And so we try to solve this. And first thing people might do is try to tackle this first problem, right? So in order to prevent slow access to the database and reduce some of that read load, you might add in a cache. Maybe it's Redis or memcached or something like that. And that works for read heavy kind of workloads, especially when you've got data that doesn't change much. Like maybe you've got blog posts, for example, they rarely change, but the comments might change relatively frequently, or the votes or something like that. So when our application wants to go and update something, it's going to have to read from the cache. If it's not there, read from the database, and then it's going to modify it in memory locally, and then go and update both the cache and the database, right? So we've got this kind of dual read, dual write type of flow. There are problems here as well. First of all, we've introduced a cache, or cache as some people pronounce it. We've introduced a cache, and now we have this problem. In computer science, people say that there are two hard problems: naming things, cache invalidation, and off by one errors. So now we have that cache invalidation problem. And as a side note, Orleans obviously doesn't solve the naming thing problem, but we'll get to that. So there's extra complexity in our application as well, because now we have that dual read, dual write kind of workflow. And we still haven't solved write contention at all. So we have extra infrastructure to manage. We actually even have potentially more write contention because you read from the database or from the cache. There's a time lag between writes going in here and reads coming out from here. And so write contention is not made any easier.
Yeah.
So one way to solve that is we go and add a queue. So we add a queue into the picture and we say, all right, when we want to update some data, we're going to push a job onto this queue, and then we're going to have some workers, maybe in each of these app instances, that pulls off the queue and then coordinates the write, and it's going to update the cache, update the database. And so you have these asynchronous writes, essentially. So they happen in the background outside of the user. You can do the same thing without a queue. You can use the cache or the database as a queue if you want, but the core idea is the same. You basically offload the responsibility of coordinating writes onto something else.
Right.
So what problems do we have there? Well, we still have the cache coherency problem, but now we also have slow asynchronous writes. We've reduced or maybe even eliminated write contention. So the database should be sitting mostly pretty happy, and that can scale quite far using this approach. But now we have slow asynchronous writes because writes have to go through now three or so different things, two or three at least different things in order to get there. And so from the user's perspective, they might enqueue a write, wait for it to get served by the queue, and then they might need a mechanism like polling or maybe some notification mechanism so that they know when that actual write occurred, so when it's done. And then finally, we have even more complexity here, right? We've got all this infrastructure. Don't even talk about adding service meshes to the picture to secure all the communications here, but there's a lot of stuff going on, right? And we still have these problems. So what's the cure? Well, obviously this is an Orleans talk, so I'm going to say that Orleans is the cure for these things. And what Orleans does is we say, all right, well, let's not worry about having a cache in a separate queue. We can do all that kind of caching and coordination ourselves. And it adds in these green arrows in here between your app instances. So it lets your app instances talk to each other. And by talking to each other, we can structure things in a way that makes them very efficiently cache data and coordinate writes. We don't have to have those cache coherency issues, write contention, lots of dependencies or infrastructure or retry logic for concurrency, optimistic concurrency control, for example. Instead, everything is fast, hopefully easy to understand because there's less code, and reliable. And it scales up or out as far as you need. And so this is a deep dive into Orleans. What I want to talk about is how Orleans adds these green arrows. And then when you write Orleans code, what happens behind the scenes?
Yeah. And
Okay,
before you do
so
that really
yeah,
quickly,
sure.
I just wanted to ask you a question about a possible solution, because this is something that someone's asked me about before. And when
Yeah.
we've had those issues, or when folks have had those issues of right contention, what would happen if the data was partitioned, or not partitioned even just on the database side, but from the application side? So notice you have three copies of an app in this
Mhm.
instance. And what if it was partitioned in a way that, the first one had a third, the second one had the second third, the last one had the last third. So now they're all working on different parts of the app. What would the result of that be? Would there still be problems with that, or would that be a better solution than some of those other ones?
Yeah, it's potentially a better solution, at least partitioning reads and writes. Essentially, Orleans does something kind of similar to that because you're spreading, in Orleans, you're spreading responsibility around.
Right.
But if you just say that, this app here is responsible for one third of the data and one third of the things, this another third, then now you have the problem of first of all, load balancing across them. You have to make sure they're all even. You need to have a smart load balancer to make sure that the right reads and writes go to the right places.
Hmm.
And also, if it happens that you need to touch multiple pieces of data that maybe spans partitions, then you need some way of communicating and coordinating across those partitions. So, for example, transactions are one mechanism for doing that, or workflows. And also now you have less resiliency because if each one of these is responsible for doing just one part of your data set or one part of your partition space, then if that goes down, now you've lost availability, right? So
Sure.
there are problems with that. There are ways to solve them. And Orleans essentially is one of those ways to solve them.
Got it. Okay.
Cool. So the idea there is, all right, if we have our application instances talk to each other, then we can come up with some way of solving these problems. So the first kind of question you might ask is, if you have these application instances, how are they going to find each other, right? How do they discover that there's, instance A, B, and C out there? And then what happens when we start to scale out? Like when we want to add extra instances because of load or maybe because of an upgrade or something like that, how is it going to handle that? And then finally, the trickiest question is, what happens when there's a failure? So when one of those application instances suddenly stops working, what are we going to do? Or if we shut down, maybe because we're scaling back in, how is it going to handle it? So the short answer is that in Orleans, we use a database as a source of truth. So we have this cluster membership table that sits in a database somewhere, and all of the different app instances go and talk to that. And so they say, read the table. They're essentially asking the question, who is part of the cluster of this? This cluster just means a group of application instances. And what is their status? And so it reads the table and then it might update the table to say its status, like, hey, I'm joining, I'm active, I've joined, or I'm shutting down, or now I'm gone. Or maybe, hey, someone else looks like they're not responding, maybe they're gone.
Right.
Now, this thing here, this cluster membership table, that could be Azure Table Storage or Cosmos or another traditional database, or it could be Redis, or it could be Consul or Zookeeper, or even Kubernetes CRDs. I see that Gutenberg is in the chat there, and he kindly contributed that in the Orleans Contrib organization on GitHub. So there are lots of ways that you can actually manage this cluster membership table. Now, how does that end up looking in your code? So from a developer's perspective, hopefully you don't need to know too much about all of this. Hopefully all you need to know is, I need to configure this one thing. I need a rendezvous point, right? A meeting place for all of my app instances. And back in the first video we did on Orleans on .NET, we had this application where, it was this bilingual dictionary, in case you missed it, called Hanbaobao. And in that case, we said, all right, when we're developing this dictionary locally, we're going to use some local host development clustering, which is like an in-memory, not very reliable, not good for production kind of clustering system. But then when we push it out to Kubernetes, like we did in the second video, now we're going to want to use Redis for that clustering. And so from the user's perspective, as the developer, you add this one line here, and then Orleans will manage the rest. So it'll wire up Redis clustering here, just pull the environment variable for the connection string, and Orleans will wire up clustering behind the scenes. So because this is a deep dive, we need to ask the question, like, how does that actually look? Like, how does that work? So we get this basic idea that, yep, our application instances are going to be talking to each other, and they're going to be using this database as a meeting point. So here's what it actually looks like going through this kind of a flow. So in the happy path, we've got a cluster. B is already joined, and now A wants to join. And so it's going to ask the table, the membership table, who else is around? And the table will respond, all right, well, B is here, and they're at 127.0.0.1, 5001. And so then A is going to say, all right, cool, I'm joining. And as soon as the table recognizes that, and it just acknowledges the write back to it, A is now going to say, I'm going to connect to B and anyone else who is in this thing, and I'm going to tell them what's the latest status, that I'm joining, for example. And so they establish a connection to the other nodes. So this is the process that goes on whenever a new application instance joins. So if you restart your app, or you start it for the first time, or you're adding more instances because you're scaling out, this is the flow that goes on behind the scenes when your app starts it. That's all well and good, but what happens in the case when something goes wrong? So what Orleans does is it needs to monitor the other application instances to check that they're actually still healthy, because you can't just trust that this membership table is going to be correct forever. When B says it's joining, at some point B is going to go, right? And so Orleans does this the same way that a lot of other systems do it. Like, for example, Kubernetes uses etcd as the database where they store, with strong consistency, all of your CRDs and things like that. Consul does the same kind of a thing. They all use these kinds of membership algorithms, right? And so they're all monitoring each other constantly. And so in this case, A is responsible for monitoring B, and they'll send a ping request over to B. B is supposed to respond with a pong. And so if that happens, everything is all good. There's no problem. But then someone, let's say they trip over the network cable, or a cosmic ray comes in from outer space and fries B's CPU, right? So B is now, it's totally busted, not going to be able to respond. And so A keeps sending these pings to B, but it's not getting any response back. And so this ping goes there, it times out. Another ping goes and it times out. And after some period of time, B says, okay, A says, I don't think that B is actually around anymore. And it then says, I suspect that B is down. And it writes that information into the membership table, and then it tells everyone else about that. And so essentially this is a voting process. And so the cluster of app instances, they all agree on who's around. And so if we look at the more complete scenario of when, let's say, B is down and both A and C are monitoring B, we can see how it actually gets declared as down. So A pings it a few times and doesn't get responses back. Meanwhile, C is also pinging it. So A says, I suspect B is down. And then A, once it gets acknowledgement for that, I suspect B is down. It tells C that I suspect B is down. C says, all right, so A has voted B out. Now I'm going to ping B again. And if it doesn't get a response back, then it's going to say, all right, that's 2 votes, 2 strikes, you're out, essentially. And so then it says, membership table, B is down, and it goes and disseminates that via gossip back to A. So everyone can now agree on who is around.
Nice. And so then gossip is like this just general consensus algorithm that we could use for membership, right? And so it's not just an Orleans thing, but it's like just a general algorithm that I'm guessing a lot of service discovery distributed systems use to know who's available in my network. Kind of.
Yeah, so different applications. So Consul, for example, uses an algorithm called SWIM. You can look up the research papers on how it was defined, and then they layer some strong consistency stuff on top of that using Raft. But essentially, yes, everyone uses a similar kind of an algorithm for deciding the simple question of who are my friends, right? Who else is around? So Orleans has one way it's been battle tested and run in production for 8 or 9 years now. So it's very robust and very reliable. And other systems have other ways they're reliable too. Like Service Fabric, for example, also has reliable, strong consistency membership. Now, this is all well and good, right? This essentially enables us to draw those green lines. So we've got our green lines between our app instances, but so what, right? We asked the Shania Twain bot on Twitter, these green areas, do they impress you? She ain't impressed, right? Because this is just a means to an ends. This is not an ends in itself. So now that we've actually got connection between our app instances, we have this healthy, fault-tolerant cluster. It's going to heal when an application instance goes down, and we configure it with just one line of code. Everything is great, but we need to actually do something with it, right? Ideally, we need some way of coordinating work and spreading work across our cluster of machines, right? Our big computer. And we need to describe how this actually even solves our original problem. Like, we talked about all these problems, and I just said, yeah, Orleans solves these things. So we need to actually go and describe how that works. So we have communication. Now we have to talk about this primitive that Orleans gives you. We already talked a little about grains, but there's this primitive that Orleans gives you that helps you actually solve these problems. So grains are this kind of cloud native objects, right? They're very similar to traditional objects, but they're tweaked, like I said, a little bit so that they work well in this cloud native environment. And the core idea here is that you want to be able to treat your cluster of application instances like it's just one big computer. And the way you do that is by dividing your application up into many little objects that we call grains. And so you're going to have one grain for each user profile in the system, or each shopping cart, or game session, or chat room, etc. And then each one of these grains, they have an ID. So you need some way to be able to refer to them when they're on another machine, or maybe they're not on any machine at the moment. When you're in the same process, you just use a regular pointer / an object reference, right? You don't even have to think about it. But when they're distributed, now you need to think about it. So they all have an ID. Then there's a .NET class that finds how they behave, and maybe they have some state. Maybe they have a lot of pieces of state, or maybe they don't have any state as far as Orleans is concerned. And so that might be, your gamer score and your user profile, for example. And we saw how that looked in that Handbell app in the first video. So then once we've got these grains, we need to spread them around our cluster. And this is what Orleans helps us with. So Orleans is going to make sure that when you need these grains, they're going to be loaded into memory for you. And so you can send messages to them, load up your gamer score, for example, from your user profile transparently for you. And then when you don't need them, Orleans will just unload them, because let's say it's 7 a.m., you've finally gone to sleep, you don't need to check on your gamer score anymore. And so it can free up that memory and let other people on the other side of the world, use some of that memory in your cluster. And so Orleans,
about how grains work, because I want to know how granular the grains get, right?
Yeah.
So for instance, you're using an example here in that second bullet point that a grain could represent a single shopping cart, right? And so in my head, a shopping cart could have multiple things in there, right? I have multiple items in my shopping cart. But then when I think about a user in a game, I have one user in the game, right? Not like multiple users, you know what I mean? So like, how granular should we design these grains to hold memory? Or does it just depend? Like, do some grains hold multiple things, like multiple identities? Or should I always think about a grain as a single identity of a single object in memory?
So in the case of a shopping cart, you probably don't need a grain for every single item that you have in there, because you don't really need to concurrently go and change and manage them. It's really nicer just to see them as this one thing. It's this pretty short list of a couple of different things with quantities and whatnot. And so you could think of that as one thing, or a chat room, right? You might have a Teams room with a bunch of different users in it. That can be represented by one grain. Now, that doesn't mean that grain has the entire history of chat communications that went on in there. You probably still want to keep them somewhere else. And maybe you just load the most recent ones into memory, right? But in the case of a user, let's take the example of PlayFab's monetization service. Your user in Minecraft is different to your user in some other game. Like even I think between Minecraft and Minecraft Earth, maybe they're different. They're different actual grains, but they're tied together using some common identity, right? And then grouped under, say, a tenant or a game title or something along those lines. But essentially, this problem of deciding how granular do I make these, it's a design question. And it kind of comes down to how much data is going to be inside of each one. And, will I need this data when I need that other piece of data? Like, are they logically connected? And
Yep.
also, how chatty are these things going to end up being? Like, am I going to need to answer a single request? Am I going to need to go out to like 50,000 different objects to get something back? Because obviously that's not going to be the cheapest thing in the world. But if you're just answering from a handful, a few objects for each request, then that's very cheap.
Right. So then it really just depends on your application, and I guess that makes sense.
Yeah, we
Um,
can give guidance on it, case by case basis too.
right. We have some questions coming in from the chat that I want to make sure that I acknowledged.
Mhm.
First one I want to take a look at is this one. It says when a grain is deactivated and later reactivated from storage. Because I remember you were talking about storage a little while ago.
Mhm.
Are there any gotchas you need to keep in mind to keep reactivation time as low as possible?
Yeah, that's a good question. So the main gotchas are when you activate a grain, you get access to this thing called on activate async. So it's like a essentially a life cycle hook that says
Mhm.
we're starting you up. Is there anything you need to do? And so, for example, that might be loading state from some remote service, or it could even be calling another grain, things like that. The advice I would give is try to keep that to a minimum, right? If you have lots of different disparate pieces of state that you might not need, I would probably not load them all up eagerly necessarily. And maybe if you have to go to too many different data stores to fetch all that state, that might not be the most optimal. Now those things can be done in parallel, so it's not the worst thing in the world, but still you need to measure that kind of thing.
Got it. All right. And another question coming in from YouTube. This person is asking, is there any guidance of using Orleans in the front end, especially WPF? I feel rich clients could be considered just another node.
Yeah, I haven't seen many applications that use Orleans inside of a WPF app. And I think that there's a lot you could talk about there, because you kind of have this idea of, all right, do grains represent this unit of concurrency or something like that, like they do in traditional Akka or Erlang, where you have actors for concurrency. But in .NET, you have tasks, right? So you don't need a grain just for concurrency reasons. So you can potentially host all leans inside of a WPF app. I think I've seen someone do that. I don't know if it went to production like that though. But
Mhm.
generally speaking, you keep your grains in the data center side and you communicate to them using gRPC or SignalR or HTTP or potentially even UDP or TCP.
Right. So then grains, at least from an Orleans perspective, are usually like background tasks. We could think about them like that. Like if I want to offload work from a client thing, right? Like I probably send it to a backend somewhere. It'll do the processing using Orleans, and then I'll wait for the results or the status of the update or whatever.
Yeah, well, you can use them in an interactive way. So if you have a website, like with that Handbell example, that bilingual dictionary, we were calling straight into grains or even multiple grains and getting responses back very quickly.
Yeah.
But you don't run them inside JavaScript, for example, or inside WebAssembly, at least not yet. Maybe someday it would be really fun to experiment with that kind of thing. Like, what does it look like to spread them all the way to the far edge of the network, where you have them running down on individual devices and things? I think it's a good, interesting experiment to do. But generally speaking, that's not how most Orleans applications are architected today. Usually, you keep the client separate from the service, and Orleans lives inside the service.
Got it. Okay, that makes sense. All right, we're gonna hold off on questions for now, but I'll let you go ahead and finish up with this slide.
Yeah, no worries. So we were saying that Orleans essentially manages loading and unloading your grains for you, wherever they are in the cluster, and also that it routes messages to them. So if you make a method call, like, I want to get the contents of some blog post, and you've got this blog post slash .NET perf tuning, this is a grain ID here, then every time you call that, no matter which front end you hit, it's always going to get routed to the same place in your cluster of application instances. And then the final thing is that Orleans makes each one of your grains single threaded. right? And that's an intentional choice. And the reason for it is that you want less bugs, no locks inside your application code, and you want to make it easier to coordinate writes to storage, right? So that you can have coherency there. So once we've got these things, how does that actually solve our problems? So we talk about the benefits here. Now, one of the biggest benefits straight away is that you have less reads on your database. So because all of the hot and warm data is going to be kept in memory somewhere in your cluster, and the cold data will be kept in the database, you don't need a separate cache. You don't need a separate cache for that, right? So you're alleviating read pressure on the database. The other thing is that because each grain has its own state and each grain manages writes to the database itself, you don't run into these write contention problems, right? So you're not going to have hot rows in your database that end up getting written from multiple places at once because you're coordinating them through each individual grain. And so because they keep the cache in memory, and because they coordinate writes, you don't end up with cache coherency problems. So the writes go through each grain, and it updates its in-memory state as well as the database state at the same time in a coherent way. And then by doing this, you get better scalability. And you get it for two reasons. One is because you're putting less load on the database doesn't have to be scaled out or up as far as it would. And the other reason is just because you can make better use of all of your application instances, better use of their memory, for example. And you also get low latency writes. So because you don't need to have an asynchronous queue worker or something like that to coordinate writes, you can make writes directly from your grains. And so you can make very quick writes to the database, and the database is less loaded and respond directly back to the user. So hopefully the upshot of all of this is you get some degree of simplicity. You have less infrastructure, you don't have that cache or the queue and things like that, less to manage. Hopefully less code because you don't have to have dual writes and dual reads and queue management and things like that, and less error handling and less retry logic for the same kinds of reasons. So hopefully it's relatively clear at least how that helps to solve our original problems that we were trying to solve. Yeah. We can get into the more deep dive kinds of questions that I wanted to talk about here. And in order to do that, we need to first give a kind of a 101 introduction again into how we define a grain and how do we refer to them so that we can call it. And the reason we need to do that is so that we can now talk about the more important thing that we're here to talk about, which is when you make a method call on a grain, what actually happens underneath? And if a grain is not active when we call it, or if we don't know where it is, how do our message calls and messages actually get routed to the right place in the cluster? So, we had this iDictionary entry grain from the first video for our bilingual dictionary app, and that's on YouTube, so you can go and have a look at it. But essentially, it's this simple grain, and we said we're going to have one of these for each dictionary entry. So in this case, it's an English-Chinese dictionary or English-Mandarin dictionary. And so we'll have one dictionary entry grain for, say, hello or ni hao or something along those lines. And then we have this method for getting the definition of that term. And then we have a way that we can update it. Maybe we want to edit it a little bit. So grains start with a grain interface. The next thing we have is the implementation of that. And in this case, this is a simplified version of that same grain that we saw in the first video in the series. But essentially, it's the same logic. We have some state that's associated with the grain that gets loaded automatically for us by Orleans. And then we just implement that interface over there. And so we've got our implementation of updating the definition. First of all, we update the local in-memory representation of it. And then we're going to go and write that out to the database. But for getting the definition, for doing those reads, we can just serve that straight out of memory. We don't need to go and hit the database again for that. Yeah. So that defines how a grain looks, but then how do we actually use them, right? So we need to call this getGrain method. We tell it what kind of grain we want, and then we say which word we want. So, hello, etc. And then we need to call it. We make an asynchronous method call on this reference to the grain that we got, and we get back our result. So that's essentially the superficial look at it from what a developer sees. What we're interested in today is what happens behind the scenes. So essentially, Orleans uses asynchronous remote procedure call. So asynchronous RPC. It's just like gRPC, except that first of all, because you're targeting individual objects and not entire services at a time, it's a little bit different. And also it supports generics and other .NET kind of niceties like that. But like gRPC, it generates some code for you behind the scenes. And in Orleans' case, it's going to generate two classes. So for each interface you define, there's going to be one class that turns your method calls into messages, and that's called a grain reference. And that grain reference, we'll see what it looks like in a second. That grain reference implements the interface you define. So it's going to actually implement iDictionary entry grain. And then the second thing is, now that we have messages, we need to turn those messages back into method calls. So if we're making a call across the wire, on one side we turn method calls into messages. On the other side, we turn messages back into method calls. And that's called a grain method invoker. And now when we want to get a reference to that grain, we call get grain of T with some ID. What Orleans is actually giving you in return, it's just that grain reference class. So it's just an instance of this generated class that points to that grain. Now that class that it gives you back that implements your interface, it doesn't know where exactly the grain lives. All it knows is the grain's type and its ID. And so Orleans is responsible for doing all of that plumbing behind the scenes.
Got it. Now, Reuben, man, listen, you got a whole bunch of questions coming in here now, particularly after you showed that little demo. And I want to make sure I answer some of these before we go on.
No
first question is asking, are there any F# bindings for Orleans? First question.
Yes, you can use Orleans from F#. It's not the nicest approach because the code generator runs on C#, and so there's a way to do it that we can talk about. But we actually test against F# in our regular BVTs. Essentially, you just need to offload the code generation that it does here into a different project. And so then you'll have your F# defined interfaces and some C# code that you can then load into your application that does all of the plumbing for you.
Got it. And then next question that we had that came up was, so this person's asking, is there a free persistence option? I feel like persistence support kindly pushes the user towards Azure/Cosmos. But I'm guessing you could use anything for persistence, right? And I'm guessing persistence is also pluggable. So you could write your own if you wanted to.
Yeah, there are heaps of persistence plugins. So if you have an on-prem SQL server or you want to use Redis or something like that, then there is already plugins for that. You can even write to files if you want to. But Azure Storage generally is a cheap option that you can use with free Azure credits. But also it's fairly easy to just write your own. So if you have some place to store data today, you can use that.
Got it. And then last question I'm going to hit you with before we move on. This person was asking, how does Orleans fit/conflict with Dapper? Because Dapper, if folks don't know, Dapper was released 2 weeks ago now, Vert v1. So how do those two play nicely or not together?
Yeah, that's a fair question. So there are some parts of that we're still looking into, like ways that Orleans and Dapper can play nicely together so that, you can run Orleans inside of a Dapper app, for example. Nothing really to announce there yet. But generally speaking, Dapper also has actors, just like Orleans. And in fact, the Dapper actor model is taken from Orleans. So we talked about virtual actors at the top of the show. And what Dapper implements for actors is also an implementation of virtual actors. So they have similarities in that regard. I would say Dapper, generally speaking, is, I believe, a lot more focused towards, say, integration type scenarios where you have different pieces of your app defined in different places, whereas Orleans tends to be more, I live in C# world. I define things in .NET. So, I think that maybe some clarification on messaging is something that will be forthcoming. But in the meantime, hopefully you can look at the both and decide just which one works for your scenario.
Got it. All right, cool. All right, I'll let you go ahead now.
Cool. Okay, so we've mentioned generated code. Now, you can go and download that app that we built in the first episode and get it from GitHub and then build it locally. And if you do that, you'll see that in the obj directory, we actually have some generated code. And so we can go and look at this file. Now, newer versions of this are going to use a source generator, and you can do the same thing with source generators. But in this case, It's the exact same code that gets generated here. And so we can just go and inspect that. So the first thing that we want to look at is, and forgive me for fitting a lot on this slide here, but this is what that generated grain reference looks like. So you see that we have this dictionary entry grain reference, and then you can see here it implements grain reference, and it also implements our interface. And so internally, it has one method for each of those methods in our grain reference, sorry, in our grain interface. And then behind the scenes, it's turning your method call here with your arguments into this message. So there's some object that gets created here that represents that method call and points to it, right? So this is the first part of the equation. Now, the second part of the equation is that we're then going to have that grain method invoker that takes that message and comes down here and turns it back into a method call. And so, it pulls off the arguments and actually calls that on your grain instance, right? So what does that look like in a more graphical way? Here's a drawing of it. So let's say that we've got this caller on the left-hand side, and that's got a grain reference. And so it's calling get definition. And then that definition creates a message. That message then gets potentially passed over the network and into some grain. So some magic happens in the middle here that we'll talk about in a second, but then it gets enqueued on the grain's internal message queue. And I mentioned that these grains are single-threaded. Well, that message queue is one of the ways that single-threadedness is maintained there. And so then this grain is going to go and execute those messages one by one. We saw the code for how get definition looked earlier. So here's a slightly simplified version of it. Essentially, that grain method invoker is then going to get given that message and then call this method on the grain. It just returns a state, right? So potentially another hop over the network back to the original caller. They get the definition out of this dictionary entry. And from their perspective, it just looks like this get definition asynchronous call here just completes with this, right? So they don't need to know about all the plumbing that went on in between. Now, I drew in the state here, not because it's actually going to be referenced in this case, it's just in memory here. But in general, grains have state, and they have that state stored in some database, be it Redis or wherever else. And you saw in the update case that we're actually going to write that state back to the database every time we modify it. And so under the hood, that's simply just a write call back to whatever database provider we've plugged in there.
So then,
okay, so
as I'm wondering about how, I'm thinking about the architecture of this in my head. And I can imagine on my client application, whatever it is, and I have like that grain factory, right? And I'm saying, hey, give me this dictionary entry, give me the grain that does this thing, right? And now this grain lives on another machine somewhere in outer space, wherever it is, right? And I reach into this grain, or I reference that grain, I send it a message, and I have it do some work. Now, how much information does my client app have to know about the grain? I'm guessing.
It just needs a reference to it. So however it gets that reference, that's all it needs to know. So internally, that reference doesn't know where that grain lives. That's the responsibility of Orleans. It just says, I want to message this thing. In this case, I want to message or call dict entry /hello with this call, right? Please, Orleans, you work out the rest. So as a developer, you don't need to know where this thing lives. And even the caller itself, internally doesn't need to know where this thing lives. Orleans will deal with all of that routing.
Okay.
And we can talk about how that works. So the next obvious question is, on the previous diagram here, I said that there's some kind of a hand-wavy magic that goes on in here, a potential network hop or some kind of routing. So what does that look like? Well, the real question is, how do we find grains in our cluster of app instances? The answer to that is that Orleans has something called a grain directory. And this grain directory is a lookup of, for each grain, if it's around somewhere, where exactly is it? And so you can use this inbuilt version, or you can use Redis or Cosmos DB. It's another pluggable kind of a system. And those lookups are cached, and Orleans will handle the invalidation of that. But you can think of this like DNS. So if that grain's identity, that ID dict entry /hello, is a host name, then the grain directory is kind of like DNS in that it'll go and find and resolve that host entry for you back to some address where the messaging system can go and send it.
Got it.
But then the next kind of question is, all right, well, let's say it doesn't exist anywhere at all right now. I've just turned on my fresh app. Nothing is around. Well, in that kind of case, Orleans says, all right, nothing, there's no instance of this grain around. It doesn't exist. So we need to place it somewhere. So we need to pick a place amongst all of your app instances to put it. And that system is called placement. And again, this is customizable. So you might just say, for any grain I want, just pick a random spot, like roll the dice and pick a random spot in my cluster of app instances. Or maybe you say, if this thing is not active yet, just put it right next to the caller so that we can make very quick calls to it. No network necessary. Or you can say, put on the least loaded app instance. So if you're familiar with distributed load balancing, you can go and look up the implementation of this is called a power of two choice algorithm. So you can look up distributed load balancing. You'll find that you'll come across that algorithm there. Essentially the same thing. Or in some cases, for example, there's an internal case where there's a lot of data scattered around this big set of machines, and the developer wants to make sure that this grain executes on the machine that's closest to my data. Because let's say they've got to crunch through a big data set. Maybe it's the Internet Archive, or maybe they've got a search engine. And so they can choose a custom placement provider that routes this grain and places it on the machine that physically has that data available already. But essentially, wherever your heart desires is where you can place it. So you can customize this thing very easily. It's not a lot of code to do it. If one of these inbuilt things doesn't fit. But of course, you don't have to. You can just let the inbuilt thing take it away for you, and generally speaking, everything will operate just happily.
Nice.
So again, let's put this all together. So here's kind of our picture from before, but instead of that dotted line, we've gone and drawn in some of the internal components. So our caller goes and makes this call, creates this message, and then it passes it on under the hood to the messaging system inside of Orleans. Now, the messaging system doesn't necessarily know where that grain lives. Maybe it's not even active. So it says, okay, placement, I want you to get me the location of that grain or place it, pick a place for it. Now, in this case, placement might check its local cache. It's going to consult the cache, and the cache will say, I don't know where that thing lives either. And in that case, it will say, all right, directory, I want to look up this grain. And if you're using the in-cluster inbuilt directory, then that's a distributed thing where it says, all right, you're responsible for these set of grains, and this other app instance is responsible for some other set of grains. So it's distributed around, like they share responsibility. And so in this case, it's making a call across to this other app instance, with 5555 as its port number, and saying, okay, do you know where this grain lives? Because you're responsible for it. And in this case, it says, okay, yeah, that thing lives on me. So that gets passed back to the directory, back through placement. And then placement is going to stamp that address on the message and give it back to messaging. So messaging says, okay, I know where this message goes. I'm just going to send it there. And so it sends your request to messaging. Messaging might say, okay, well, that grain, it wasn't actually active locally, but placement decided that this is where it belongs. So I'm going to go and either look it up, or I'm going to go and activate it, and then I'm going to push that message into its queue, right? And so then that grain method invoker gets called, and it executes that message, and it goes and returns a definition, flows back to the system all the way up to the caller. Now, this caller here, that could be a signaler hub, it could be an ASP.NET controller, it could be a background thread, it could be another grain. So you can have grains, call grains, etc. You can structure that however you like, and none of the flow changes at all. So nothing needs to change depending on wherever you want to call it.
Got it. And then
All
kind
right.
of what you mentioned, if I wanted
Yeah.
to, like we could kind of customize the way that placement happens a little bit. So if there's any
Mhm.
particular business reasons, right? Like I want it closer to my
Yeah.
client, or I want it on the machine with the least amount of activity on it, or
Mhm.
whatever your use case happens to be, right? Like we could kind of customize that placement a little bit to kind of figure out what's the best node, I guess, for this thing to live on.
Yeah, exactly. Yeah, and so that logic, when you customize it, it'll just run inside here. So your little bit of .NET code will execute inside of the placement provider. Maybe this type of grain has one placement provider, and maybe a different type of grain has a different one. And so you can customize that on a granular level if you want.
Got it. I wanted to
So,
ask you a little bit
yeah, sure.
about scaling. Um,
Mhm.
so so you showed, I think in your first or second slide, in the first few slides you showed how we kind of boot up Orleans, right? You showed like there was like a silo host and like a host builder type
Yep.
pattern that we used to kind of boot this thing up. So
Yep.
I'm guessing every Orleans stakeholder that's inside of that cluster has to have a copy of that same host. So as you scale, am I just copying that same host around? Is that what's happening?
So if you scale to multiple instances, that's just means that you're executing, the same myapp.exe, or obviously on Linux as well, it's not going to have a .exe, but you're just executing that same thing on a different physical host or a different container instance, for example. So in the Kubernetes case, you'll go and update your deployment manifest to say, now I want 20 replicas or 50 replicas or 5 replicas or whatever it is. In
Yeah,
the Azure App Services case, you may be dragging the slider to the right, so to speak, or maybe it's managed for you, and you've got horizontal pod auto scaling in Kubernetes, or automatic scaling in App Service, or maybe you've hooked it up to Kita, right? So Kubernetes event driven
yeah,
auto scale. However you've done it, it's just launching multiple copies of your thing. Then they coordinate, they form a cluster, and then they share the responsibility.
got it. We have a question coming in really quickly from YouTube.
Yeah.
This person's asking if one of those machines where grains live fails in the middle of a chain of grain communication, how is it handled?
That's a good question. So essentially, imagine that this grain here, it tries to make a HTTP call, but then that call fails. Now, because we want these things to act just like regular C# .NET objects, the most natural way of handling that would be that you get an exception. And so if this fails with an exception, then by default, if you don't have a try catch around that, like maybe you want to have a try catch to return an error code instead of an exception, you could do that. But if you don't, then that exception will just bubble all the way up. So it could be as many levels deep as you want, and it will bubble up. Now, let's say you wanted a generic kind of general purpose exception handler. What I haven't drawn in here is that similar to ASP.NET, you can have request filters, right? So you can have a filter that goes on the incoming messages, or you can have a filter that goes on outcoming messages. So you might say there, okay, I want to retry that message because it failed. Maybe I'll back off a bit and retry. Or on the incoming side, you might do a similar thing. Or maybe you just want to log it on the way out, right? If it failed, for example. And so you've got a couple of different strategies there. But the short story is that exceptions propagate all the way back up the chain.
Got it. All right. We're running low on time, but I do want to ask at least one more question. And this one is
Mhm.
also coming in from YouTube. Dominic's asking, or he's saying, I believe Orleans is a great choice to build an entire system. Is it a good choice to build a part, like an individual microservice? And I'm guessing an individual as in like one microservice in a collection of many.
Yeah, definitely. So Orleans happily co-hosts alongside other services. So if you want to use it as part of a larger application where maybe you've got something that's written in even like classic ASP.NET, or whatever the case may be, if you want to do something in a different system, maybe it's Akka.NET, right, or maybe Dapper, or something like that, then you can happily do that. You can put an HTTP front end or a gRPC front end here, and you can communicate with your cluster of servers just like that, just this one thing. And Orleans will handle scaling all of that internally, right, or distributing that internally. So, I think it works well in that scenario as well. For example, I believe Azure IoT Digital Twins, they use Orleans as well. And so they use it for one of their core services, but they have other services which are not built using Orleans. And so they can communicate using gRPC or HTTP to that.
Nice. Got it. Got it. All right. You got any more stuff?
Just to recap, so to kind of cap this all off, we learned that grains are cloud native objects. They help us build scalable apps, and the core way of doing that is by dividing our app up into these small objects that then get distributed across our app instances. And in order to allow that to be distributed, Orleans needs to form and maintain this cluster, right? And so it connects your app instances together. It adds those green arrows into your architecture diagram. And in order to do that, it uses central storage as a source of truth, gossips updates around, and each instance monitors a bunch of others. Unhealthy ones are removed. Under the hood, all your calls are using RPC, and we saw the generated classes that are involved for turning method calls into messages and vice versa. And Orleans will manage the lifetime of your grain. So it'll load them into memory as needed. It'll send messages to them, let them handle message calls. And then when they become idle, because you've gone to sleep and it's 7 a.m., then they'll unload them and free up the memory for others. And we saw how that works under the hood with placement and directory. So that's all I wanted to talk to you about today. You can see us on GitHub here. If you have any questions or want to contribute, we love all PRs. Or you can come and chat with the team and the community here on Gitter. So we have a nice, warm, friendly community on Gitter, as well as updates and things on Twitter at the MSFT Orleans account. And you can see my personal Twitter account there as well.
Nice. And then for those that are checking out, I placed it in the chat. And also, if you're looking at the window right under here, you can see I shared the link to Reuben's GitHub repo, which has that that sample that he was talking about a little bit earlier today. One last question, because we have a little bit of time. We could squeeze out a little bit more. And I'm going to share this really quickly. And the question is, are there any best practices to follow when designing grains?
Yeah, for sure. So there is a best practices FAQ style page in the Orleans docs. And I could probably link that. Maybe I'll drop it into chat once we're done. Or if you want to message me on Twitter or on this Gitter chat room, I can drop it there. And you can see it kind of goes down in a very point by point, very punchy style about, do this, don't do that. Think about this type of thing.
Awesome. All right. Well, hey, Reuben, this has been great, man. Thank you so much for coming on. Like you and I have spoken about Orleans a few times, but every time I speak to you, I feel like I keep learning more and more stuff. So we're gonna have to do some more videos about Orleans so we could keep spreading the word and letting everyone know. Thank you, everyone, for joining us. I know we have a lot of folks from all over the world. I've seen some folks in here from India, some folks from the UK, some folks from South America, North America. So definitely appreciate those of you that are here and are up pretty late in your time zone. And thank all of you that are again here and on the other side of the world. Thank you for spending your afternoon with us. And hopefully you join us again next week. This is Microservice March. So for the rest of the month, we're going to be talking about different microservice patterns, cloud native patterns, and those types of things. So if that's interesting to you, please go ahead and join us for next Thursday, and that's Thursday after that, and Thursday after that. So thank you all so much. Appreciate it. Again, thank you, Reuben. And I hope everyone has a good day. Bye.
Take care. See you.